In our last example of a volume problem involving our rectangular boxes, we're building a trunk, or basically it's going to look similar to two open boxes just sitting on top of one another. And so in this one, it says that we have a 20 by 30 inch sheet of material, and it says the first material is folded in half. So right along here, it was 20 by 30, but they're folding it in half so that from here to here is just going to be 15 inches. And then it says that they're going to cut 4 equal squares of side length from each corner of the folded sheet. So this folded piece kind of runs along here, and they're cutting out these little squares, which in turn, since it's folded in half, is going to cut those same little squares out of this other half of the material. And so then we end up with these two shapes that look exactly the same, and these flaps that are on these are exactly the same on each half of this material. So again, we could fold along the dotted lines. We get a box that's connected here in the middle because we didn't separate it, but otherwise it would look like two empty boxes just sitting on top of each other. And so we again took out this unknown amount, x, on each side, but remember we split this 30 in half, so this was now 15, so this flap is 15 minus, there's an x here and an x here, so minus 2x, and this side is 20 minus 2x, and of course again our height is just x. So our volume equation is x times 15 minus 2x times 20 minus 2x. Oh, I'm sorry, I misspoke there. The height is x for each box, but remember there's x here and x here, so that's a total height of 2x. So 2x, so we need to put a little 2 in front of that because we've doubled the height because we're putting the boxes on top of each other. All right, so that's the equation that we can type into our calculator. All right, so here it is in the calculator, 2x times 15 minus 2x times 20 minus 2x. For this one, I set my window -1 to 10, and for my y's -10 to 1,000, and since it was a larger value, I changed my scale to 100, so I wouldn't have quite so many marks on there. Let's just see what we get. Okay, we get the part that's important to us. We probably could set this a little lower and further out to see this part where it comes back up, but it looks like it comes up, goes down, and then we have the negative values that are not really relevant to our situation. So I think it is good enough for what we need. We just need this portion anyway. So we're going to find that intersection. 1, 2, 3, 4, 5, 6, 7. It looks like a little more than 7. So I'll go ahead and draw that on here. All right, let's go ahead and find that and make sure I've got that in the right spot. So second, calculate the 0. So it says that x is 7.5. All right, and then we're going to find our maximum. So second, calculate the maximum. Go left and right of that point. And it says 2.829, 758.076. So around 2.8, and then we're going up 10 to 100. 2, 3, 4, 5, 6, 7, 8. So somewhere in here, we've got the point 2.829, 758.076. All right, so remember it's coming up from here, comes back down, goes below, goes back up, again, irrelevant to our situation. So this part is what we are concerned with. And so it wants us to find the dimensions of the trunk. So we're going to start with this 2.829. Now none of these dimensions, the length, the width, and the height, are just x. So our height is going to be 2 times this, 2 times 2.829. And so we're going to get, let's see, 5.658 inches. And then for our next dimension, we've got 15 minus 2 times 2.829. And that one is 9.342 inches. And then for our third dimension, we're going to have 20 minus 2 times 2.829. And we get 14.342 inches. So those are our dimensions. 5.658 inches by 9.342 inches by 14.342 inches. And then it says, what is the maximum volume? Well, our volume, remember, is our Y value, and our highest Y value is 758.076, and that's going to be in cubic inches. So we also should get about that same number if we multiply length times width times height. We rounded, so not exact, but that's where the numbers come from.